was squeezed to increase its density by simultaneous detonation, as with the Trinity test detonation 3 weeks earlier, of the conventional explosives placed uniformly around the pit. The explosives were detonated by multiple exploding bridge wire detonators. It is estimated that only about 20% of the plutonium underwent fission. The rest, about 5 kilograms, 11 pounds, was scattered. An implosion shock wave might be of such short duration that only part of the pit is compressed at any instant as the wave passes through it. To prevent this, a pusher shell may be needed. The pusher is located between the explosive lens and the tamper. It works by reflecting some of the shock wave backward, thereby having the small-scale slow-motion cutaway off-shaped charge implosion device. Effect of lengthening its duration. It is made out of a low-density metal such as aluminum, beryllium, or an alloy of the two metals. Aluminum is easier and safer to shape, and is 2 orders of magnitude cheaper. Beryllium has high neutron reflective capability. Fat Man used an aluminum pusher. The series of roller experiment tests of implosion-type fission weapon design concepts, carried out from July 1944 through February 1945 at the Los Alamos Laboratory and Armored Site 14.3 kilometers, 8.9 mi, east of it in Bayo Canyon, proved the practicality of the implosion design for a fission device, with the February 1945 tests positively determining its usability for the final Trinity /Fat Man plutonium implosion design. 18. The key to Fat Man's greater efficiency was the inward momentum of the massive U-238 tamper. The natural uranium tamper did not undergo fission from thermal neutrons, but did contribute perhaps 20% of the total yield from fission by fast neutrons. After the chain reaction started in the plutonium, it continued until the implosion reversed the momentum of the implosion and expanded enough to stop the chain reaction. By holding everything together for a few hundred nanoseconds more, the tamper increased the efficiency. Plutonium pit. Flash X-ray images of the converging shock waves for me during a test of the high explosiveness system. The core of an implosion weapon, the fissile material and any flector or tamper bonded to it is known as the pit. Some weapons tested during the 1950s used pits made with U-235 alone, or in composite with plutonium-19. But all plutonium pits are the smallest in diameter and have been the standard since the early 1960s. Casting and then machining plutonium is difficult not only because of its toxicity, but also because plutonium has many different metallic facies. As plutonium cools, changes in phase result in distortion and cracking. This distortion is normally overcome by alloying it with 30-35 mol, 0.91.0% by weight, gallium, forming a plutonium-gallium alloy, which causes it to take up its delta phase over a wide temperature range. 20. When cooling from molten, it then has only a single phase change, from epsilon to delta, instead of the 4 changes it would otherwise pass through. Other trivalent metals would also work, but gallium has a small neutron absorption cross-section and helps protect the plutonium against corrosion. A drawback is that gallium compounds are corrosive, and so if the plutonium is recovered from dismantled weapons for conversion to plutonium dioxide for power reactors, there is the difficulty of removing gallium. Because plutonium is chemically reactive, it is common to plate the completed pit with a thin layer of inert metal, which also reduces the toxic hazard. 21. The gadget used galvanic silver plating. Afterward, nickel deposited from nickel tetracarbonyl vapors was used. 21. Gold was preferred for many years. Recent designs improve safety by plating pits with vanadium to make the pits more fire-resistant. Levitated pit implosion. The first improvement on the Fat Man design was to put an air space between the tamper and the pit to create a hammer-on-nail impact. The pit, supported on a hollow cone inside the tamper cavity, was said to be levitated. The three tests of Operation Sandstone, in 1948, used Fat Man designs with levitated pits. The largest yield was 49 kilotons, more than twice the yield of the unlevitated Fat Man. 22. It was immediately clear that implosion was the best design for a fission weapon. Its only drawback seemed to its diameter. Fat Man was 1.5 meters, 5 feet, wide vs 61 centimeters, 2 feet, for Little Boy. The Pew 239 pit of Fat Man was only 9.1 centimeters, 3.6 in diameter, the size of a softball. The bulk of Fat Man's girth was the implosion mechanism, namely concentric layers of U-238, aluminium, and high explosives. The key to reducing that girth was the two-point implosion design. Two-point linear implosion. In the two-point linear implosion, the nuclear fuel is cast into a solid shape and placed within the center of a cylinder of high explosive. Detonators are placed at either end of the explosive cylinder, and a plate-like insert, or shaper, is placed in the explosive just inside detonators. When the detonators are fired, the initial detonation is trapped between the shaper and end of the cylinder, causing it to travel out to edges of the shaper where it is diffracted around edges into the main mass of explosive. This causes detonation to form into a ring that proceeds inward from the shaper. 23. Due to the lack of a tamper or lenses to shape the progression, the detonation does not reach the pit in a spherical shape. To produce the desired spherical implosion, the fissile material itself is shaped to produce the same effect. Due to the physics of the shock wave propagation within the explosive mass, this requires the pit to be a prolate spheroid, that is, roughly egg-shaped. The shock wave first reaches the pit at its tips, driving them inward and causing the mass to become spherical. The shock may also change plutonium from delta to alpha phase, increasing its density by 23%, but without the inward momentum of a true implosion. The lack of compression makes such designs inefficient, but the simplicity and small diameter make it suitable for use in artillery shells and atomic demolition munitions. ADMs, also known as backpack or suitcase in nukes. An example is the W-48 artillery shell, the smallest nuclear weapon ever built or deployed. All such low-yield battlefield weapons, whether gun-type U-235 designs or linear implosion Q-239 designs, pay a high price in fissile material in order to achieve diameters between 6 and 10 inches, 15 and 25 centimeters. Hollow pit implosion. A more efficient implosion system uses a hollow pit. A hollow plutonium pit was the original plan for the 1945 Fat Man bomb, but there was not enough time to develop and test the implosion system for it. A simpler solid pit design was considered more reliable, given the time constraints, but it required a heavy U-238 tamper, a thick aluminium pusher, and 3 tons of high explosives. After the war, interest in the hollow pit design was revived. Its obvious advantage is that a hollow shell of plutonium, shock deformed and driven inward toward its empty center, would carry momentum into its violent assembly as a solid sphere. It would be self-tamping, requiring a smaller U-238 tamper, no aluminium pusher, and less high explosive. Fusion boosted fission. The next step in miniaturization was to speed up the fissioning of the pit to reduce the minimum inertial confinement time. This would allow the efficient fission of the fuel with less mass in the form of tamper or the fuel itself. The key to achieving faster fission would be to introduce more neutrons, and among the many ways to do this, Adding a fusion reaction was relatively easy in the case of a hollow pit. The easiest fusion reaction to achieve is found in a 50-50 mixture of tritium and deuterium. 24. For fusion power experiments, this mixture must be held at high temperatures for relatively lengthy times in order to have an efficient reaction. For explosive use, however, the goal is not to produce efficient fusion, but simply provide extra neutrons early in the process. Since a nuclear explosion is supercritical, any extra neutrons will be multiplied by the chain reaction, so even tiny quantities introduced early can have a large effect on the outcome. For this reason, even the relatively low compression pressures and times, in fusion terms, found in the center of a hollow pit warhead are enough to create the desired effect. In the boosted design, the fusion fuel in gas form is pumped into the pit during arming. This will fuse into helium and release free neutrons soon after fission begins. The neutrons will start a large number of new chain reactions while the pit is still critical or nearly critical. Once the hollow pit is perfected, there is little reason not to boost. Deuterium and tritium are easily produced in the small quantities needed, and the technical aspects are a trivial. 24. The concept of fusion-boosted fission was first tested on the 25th of May, 1951, in the item shot of Operation Greenhouse, in Iwatak. Yield 45.5 kilotons. Boosting reduces diameter in 3 ways. All the result of faster fission since the compressed pit does not need to be held together as long. The massive U-238 Tamperkin be replaced by a lightweight beryllium shell to reflect escaping neutrons back into the pit. The diameter is reduced. The mass of the pit can be reduced by half, without reducing yield. Diameter is reduced again. Since the mass of the metal being imploded, tamper plus pit, is reduced, a smaller charge of high explosive is needed, reducing diameter even further. The first device whose dimensions suggest employment of all these features, 2-point, hollow pit, fusion-boosted implosion, was the Swan device. It had a cylindrical shape with a diameter of 11.6 in, 29 centimeters, and a length of 22.8 in, 58 centimeters. It was first tested standalone and then as the primary of the two-stage thermonuclear device during Operation Red Wing. It was weaponized as the Robin primary and became the first off-the-shelf, multi-use primary, and prototype for all that followed. After the success of Swan, 11 or 12 inches, 28 or 30 centimeters, seemed to become the standard emitter of boosted single-stage devices during the 1950s. Length was usually twice the diameter, but one such device which became the W-54 warhead, was closer to a sphere, only 15 inches, 38 centimeters, long. One of the applications of the W-54 was the Davy Crockett XM388 recoilless rifle projectile. It had a dimension of just 11 inches, 28 centimeters, and is shown here in comparison to its Fat Man predecessor, 60 inches, 150 centimeters. Another benefit of boosting, in addition to making weapons smaller, lighter, and with less fissile material for adjuvant yield, is that it renders weapons immune to pre-detonation. It was discovered in the mid-1950s that plutonium pits would be particularly susceptible to partial pre-detonation if exposed to the intense radiation of an Irvine nuclear explosion. Electronics might also be damaged, but this was a separate problem. RI was a particular problem before effective early warning radar systems because a first strike attack might make retaliatory weapons useless. Boosting reduces the amount of plutonium needed in a weapon to below the quantity which would be vulnerable to this effect. Two-stage thermonuclear. Ivy Mike. The first two-stage thermonuclear detonation, 10.4 megatons, November the 1st, 1952. Pure fission or fusion-boosted fission weapons can be made to yield hundreds of kilotons, at great expense in fissile material and tritium, but by far the most efficient way to increase nuclear weapon yield beyond 10 or so kilotons is to add a second independent stage, called a secondary. In the 1940s, bomb designers at Los Alamos thought the secondary would be a canister of deuterium in liquefied or hydride form. Fusion reaction would be DD, harder to achieve than DT, but more affordable. A fission bomb at one end would shock compress and head near end, and fusion would propagate through the canister to far end. Mathematical simulations showed it would not